Hey guys, today we're talking about rotational mechanics with emphasis on torque and rotational equilibrium. So, in a problem where we're dealing with some kind of rotation, torque is the thing that causes that rotation. When force is applied, it causes a rotation. We call that torque. I'm getting through here. In rotational motion, torque is more closely related to the motion and not necessarily the force that's applied to it. So it's describing a rotation that's caused by a force. It's not the same thing as what the force actually is. It's a common misconception. So when we're dealing with an object that's moving, we've got a couple of different ways that it can move. A lot of times we'll deal with something that's just a translation. So it's just sliding. I'm pushing a box along, or in this case, I'm just sliding the ball from one position to another. We also could have a rotation. That's when our object spins. The center of rotation is kind of what we call that line or that point where it turns about. So our kind of our center of rotation, our axis of rotation is another thing that we could call it. That's just what we describe as where it's spinning about, where it's spinning around. And it also could do both. So kind of a more likely scenario is that the ball is doing both. It's rolling along the floor or rolling along whatever path it's following. It's both rotating and translating. So rotation means it's spinning about an axis. Translation just means it's changing positions in space. So the way that we look at torque, we'll look at a lot of these problems, a lot of wrench problems, a lot of kind of applying a torque to a rotation. There's a lot of different applications to it. Anytime you've got a hinge, you've got a thing that you're spinning around or turning it, we've got torque happening. But when we're doing that, the way that we're pushing or pulling, depending on which direction we're going, we have what's called a line of action, which is like in order for us to be causing a torque, in order to cause a rotation in this scenario, we have to make sure that the way that we're pushing or pulling can't go through that line of action, can't go through my center. Because otherwise, if you've ever tightened a wrench or done any kind of thing, if you're pushing the wrench straight into the bolt, you're not going to cause a rotation unless you're applying that force at some kind of an angle from that center. So it's that imaginary line that follows the direct path of the force and applies through its point of application. So right here where your hand is holding onto the wrench, that's the point of application, which will be very important because when we look at our equation for how we calculate this, we have to kind of maximize that distance. So we have this thing called the lever arm. It's a little bit different than the radius that we'll look at in a second. It's not necessarily the same thing as where your hand is applying the force to, because the lever arm is that distance away from your line of action to the center of rotation. So that line of action always has to be perpendicular to your center. So in order to maximize your force that's being applied, you want to apply that force perpendicular to your actual thing that's rotating, your lever, your wrench, your hinge, whatever. So that R can be the same thing as the distance between where you're applying the force to that center of rotation, but it also could not be depending on how that angle is applied. Which this is just re-emphasizing that again. Your line of action is that direction of your force, whether it's pushing or pulling. Your center of rotation is where you're spinning about. And then your lever arm is that perpendicular distance between your center of rotation and that lever arm, that line of action. So once we know those two things, once we know what our different values are, we can actually get into the equation, which torque, which we use a lowercase t for torque, is simply our radius, which is our lever arm length, times the force that's being applied. So we have our radius, again, sometimes, depending on how it is, how that action is applied, that line of action is lined up, it could be the distance between the center of rotation and where you're applying the force. In most cases, that is going to be the case. We're assuming we're trying to maximize the force applied. So that it's just your radius times the force that you're applying. It's as simple as that. Now we do have, because it's a force, we have both positive and negative, right? Force is a vector. So in this case, our torque has value that is positive and negative. And you can see the direction that you're causing that rotation to happen determines whether it is positive or negative torque. So a clockwise rotation, so causing it to go the same path as what a clock usually goes, is negative. Causing a counterclockwise rotation is positive torque. And it seems counterintuitive, but when you look at it in the math side of things, I know if you're currently in Algebra 2, we haven't gotten to this yet, but for those who have already completed Algebra 2, if you think back to those angles in standard form, where we have like our terminal and initial side, that rotation is always based on, if you imagine a XY plane in your graph. So like here, if this center of rotation happened, if this is X, Y, you're going up from that initial side, so you're causing that positive rotation if you're going counterclockwise, where here, if I were to draw this, if I'm going this direction, I'm causing a negative rotation. So again, those angles in standard form, that's what it goes back to. That's kind of the rationale behind it. That was at least how I remember it. If you need to just memorize that clockwise is negative, counterclockwise is positive, then so be it. So different things that affect torque. The distance, obviously, how far away your force is applied at is going to change how much that force impacts the rotation. So the further away you are, the less you have to actually apply a force to get that same torque. Other things that affect it, the angle. Again, we talked about wanting to maximize that force. If you're trying to get the most amount of torque out of the same amount of force, your best option is to get it perpendicular to it. Where if we have something like this, where it's not applied at 90 degrees, this d, this distance between your center of rotation, and your applied force is not the same as your radius. Because this, again, distance from the center of rotation to that line of action is going to be what the radius we would have to use is. So, and that's not the same. And then obviously our force, if we can apply more force, it's going to cause more torque. This is directly proportional to the force, meaning if we increase the force, we increase the torque. If I have a bigger force than another one, I have a bigger torque than the other one. So jumping into an example problem here, just calculating torque. If we've got a force of 50 newtons applied to a wrench that is 30 centimeters long, we're asked to calculate the torque if the force is applied perpendicular to the wrench, so the lever arm is 30 centimeters. So this is just a diagram of what's going on. What we have to be careful of here, our standard unit for radius, for our distance, is meters, not centimeters. So we're going to have to do a conversion here. But let's go ahead and jump into actually doing this. Make sure my pen is all set up to go. All right, so we have our formula. T equals R times F. So we have to make sure our radius, since we're dealing with 30 centimeters, that is 0.3 meters. 0.3 meters. Our force, they told us, was 50 newtons. So 50 times 0.3 should be negative 15. Here, whether it's positive or negative, it's kind of, based on how you assume the rotation is happening. If you look back here, based on the diagram that they're giving us pulling on the wrench instead of pushing on the wrench is what determined that this should be a negative rotation instead of a positive rotation. But otherwise, yeah, 50 times 0.3 just gives us 15 Newton meters. And that should be our units, Newton meters. No, yep, negative 15 Newton meters. Okay, jumping into our next one, torque and seesaws. So this is kind of where that balancing act comes into play. We'll actually get into the formula for it in just a little bit, but just talking about seesaws in general, we have in a seesaw, the point where it's balanced at is called the fulcrum. It's just where that rotation happens. So when we have something called equilibrium, we talked about equilibrium with center of gravity last week. With if we have to raise or lower, or our center of gravity stays the same, that determines whether it's static. What is it? Static, positive or no equilibrium. Stable or unstable, not yes or no. Stable equilibrium, unstable equilibrium, or static equilibrium. So at equilibrium here with our rotation, or our seesaws at least, we have kind of two different things that determine whether it's in equilibrium. We have equilibrium for our translational, which we'll talk about in a second. There's no net force acting on it, so pushing and pulling. Our seesaw is not lifting up or sliding down the fulcrum. And then we also have our equilibrium of rotation, which would be there's no net torque acting on our object, on our seesaw. It's not causing rotation back or forth. So if we're in true equilibrium, we have no net torque, we have no net force. So that means all of our torques have to be balanced, all of our forces have to be balanced to be at equilibrium. So again, our sum of all the forces have to be equal. This is just a fancy way of looking at it. You've got the formula if you need it. If you don't, whatever. In general, I don't use these formulas kind of explicitly. It's more so just knowing that all of our forces have to add up to zero, all of our torque has to add up to zero. Because again, we have these two different types of equilibrium. If we have translational equilibrium, that just means it's not raising or lowering off of the fulcrum. So all of those net forces have to be equal. So our two forces pulling down and our frictional force, or our fulcrum force at the fulcrum, are what would be a normal force in this case, pushing up against the board, would have to be zero if we balance those out, right? One big positive, two smaller negatives. Same thing with our rotational equilibrium. Again, a force acting in either direction, or a torque that's caused in either direction, has to just be balanced. We know that it's not going to necessarily be zero on both sides. It's probably going to be one force or a torque on one side, a torque on the other side, and because they're causing different rotations, one's positive, one's negative, they're going to add up to zero. Now, in general, again, that's how we would calculate our balancing act stuff. So our distance away times the force that's acting. So that's, again, how we would use, what formula we would use. Our torque formula would be distance times force, which on the balancing act one, you could have simplified that down to just your mass times your distance, your radius away. This is a nice little shortcut since it's going to be gravity on both sides. All right, so let's go ahead and use a problem here, do a problem with that. So we've got a boy and his pet cat. Very exciting life he lives. His cat has a mass of 4 kilograms and is sitting 2 meters from the center of rotation. If the boy has a mass of 50 kilograms, how far away does he have to sit so that the seesaw will be balanced? So, again, I'm going to go ahead and jump forward here. So if we've got rotational equilibrium, we want to make sure that I need to turn my pen back on here. Here we go. So the torque of the cat has to be equal and opposite of the torque of the boy. So starting with the things that we know for the cat, our torque is going to be our force times distance. Same thing for the boy. We don't have the forces that are given to us. We're just given their masses. So we're going to have to use mass times acceleration for their force. So the cat has a mass of 4 kilograms times 9.8 meters per second for acceleration due to gravity. And it is sitting a distance of 2 meters away from the fulcrum. The boy has a mass of 50, so a whole lot more massive, times 9.8 times, we're trying to figure out that distance away. So if we go through and do those calculations, we end up with 78.4 Newton meters on the left, and then this is going to be, it doesn't really matter again which one you say is which. The cat was on the left side, so it would be causing a rotation down on the left, which is a positive torque. So we're going to say that the boy has a negative torque, negative 490 times that distance. So we're going to have to divide by negative 490 on both sides. And we end up with a distance of 0.16 meters, or 16 centimeters away from the fulcrum is where that boy has to sit. Moving on to our last idea here. When a force is not applied at a lever arm, it is not perpendicular to the force. We have this adjusted formula to account for that. It's very, very similar to work done at an angle, where we had that force applied at an angle. It's still our force times our distance. It's just that here our radius is not the same thing as our lever arm. In this case, it's not our distance applied. So distance on the little lever arm here, I'm not highlighting the right thing. So this distance is not my radius. It's the point of rotation out to that point of action is that distance, and then times the cosine of whatever the angle is. So that 30 degrees is not necessarily always 30 degrees. It's because in this case, you're applying that angle at 30 degrees. So here, if we got a problem, a 20 centimeter wrench is used to loosen a bolt. The force applied is 0.2 meters from the bolt, right? That's 20 centimeters. It takes 50 newtons to loosen the bolt when the force is applied perpendicular to the wrench. How much force would it take if the force was applied at a 30-degree angle instead? So here, before I jump into the actual problem, we have to figure out first what torque is required in general to loosen it. So if we know 0.2 times 50, right, that's our distance times our force applied, that's how much torque would be required in this case, just normally under perfect conditions perpendicularly. So we'll use that to work backwards to figure out what force we'd have to apply at 30 degrees instead. So again, doing that first part of our problem, our torque is 0.2 times 50, which means we need 10 Newton meters to loosen the bolt in general. So if I have an adjusted formula, still 0.2, we don't know what that force applied is going to be, right? Times cosine of 30. We're going to have to solve that equation for our force. So if 10 equals 0.2 times F times the cosine of 30, solving that equation, 10 divided by 0.2 divided by the cosine of 30, we end up with a force of 0.173 newtons. Nope, sorry. 0.73 is 0.173 is 0.2 times cosine is the notes that I have written here. So we actually end up with 58 newtons, which makes sense. If we're acting in an angle, it's not perfectly perpendicular. We're going to require more force just in order to counteract that 30-degree deficit that we're dealing with. All right, that is all I have for you guys for today. As always, if you have any questions, concerns, thoughts, ideas, hopes, or dreams, make sure you guys reach out and let me know. Otherwise, have a fantastic day. We'll see you soon.